In this example, we have a ball twirling on a string. It's twirling in a circle, and the string goes down through a tube. When you pull down on the string, the radius of the circle decreases. We're given that the initial radius of the circle is 34 centimeters, and the speed of the ball as it twirls in the circle is 3.2 meters per second. Then the string is pulled down so that the radius decreases to 12 centimeters. And the question is, what's the speed of the ball with that radius of motion? Well, the mass is traveling in a circle, so we have to deal with the conservation of angular momentum. And remember, angular momentum is mvr. So if angular momentum is going to be conserved, then mvr before the string is pulled has to equal mvr after the string is pulled. Can we use this equation? Well, let's see. We don't know the mass, but we do know the speed before the string is pulled. That's the initial speed, 3.2 meters per second. We also know the radius before the string is pulled. That's the initial radius, 34 centimeters. We'll convert it to 0.3 meters to get things into the correct units. All right, we don't know the mass once again, and we don't know the speed after the string is pulled, but we do know the radius. The radius after the string is pulled is 12 centimeters, or 0.12 meters. Now look what happens. The mass cancels. So it doesn't matter that we didn't have it. It appears on both sides of the equation, so it just cancels out. Once the mass cancels, the only thing we don't know is v after, so we can solve for it. We solve for it by dividing both sides by 0.12 meters. When we do that, we see that meters cancel, and we find that v after is 9.1 meters per second. So think about what happens here. The ball is spinning around, and then the radius decreases. In order to conserve angular momentum, the speed has to increase as a result. It increases from 3.2 meters per second to 9.1 meters per second.